Okay, this is chapter 9, topic 7, graphing rational functions. All right, looking at the graph of rational functions here. Now, the most basic rational function is the parent function. Now, everything we see is going to be some transformation of the parent function, which the parent function for rational functions is just 1 over x. Okay, remember a rational function is just a fraction with polynomial in the numerator, polynomial in the denominator, and this is the most simple polynomial that we can have in the denominator is just x. So 1 over x, there are other types, but this is the one we're going to be looking at. To give you an idea of what this looks like, if we head over to Desmos and graph it, we're going to graph it by hand in a second, but you can see this is what 1 over x looks like here. A couple of things that you can tell, and maybe it will make sense that 1 over x looks this way. But you can see that there's actually two asymptotes. All right, there's a vertical asymptote, which is here at 0, and there's also a vertical asymptote here at 0. There's also a horizontal asymptote at 0 as well. And if you think about why that is, and why the function looks this way, you just have to think about what happens when you plug in specific x values. Okay, if you look at the right side here, if you plug in x values into this function, as your x values get bigger and bigger, the function itself actually gets smaller and smaller close to 0. Plugging in 2 gives you 1/2, plugging in 3 gives you 1/3, 1/4, 1/5, 1/6, gets closer and closer to 0. However, if you plug in fractions, and this is where the graph goes up like this, if you plug in fractions, this actually gets really big. Okay, if you plug in like 1/2, 1 divided by 1/2 is 2. If you plug in 1/3, 1 divided by 1/3 is 3. So as you plug in smaller and smaller fractions, this gets bigger and bigger, and that's why it goes up over here. Why it gets really big over here and gets really small over here. Now the negatives actually work in the same way. If you plug in really large negative numbers, then this graph gets closer and closer to 0. This becomes a smaller and smaller negative. Okay, so like you plug in -1, you get -1. You plug in -2, you get -1/2. You plug in -3, you get -1/3. So this just gets closer and closer to 0. Same thing is happening over here. However, if you plug in fractions, then this becomes a bigger and bigger negative. So like you plug in -1/2 and you get -2. Plug in -1/3 and you get -3. So this is kind of why this graph has this shape, is just because what happens when you plug in certain x values. Now all the graphs that we're going to do are going to be some sort of transformation of this. So it's going to be moved either up or down. So this graph could be somewhere else, and we're going to look at that on the graph in a second. Now, the transformations we are going to be looking at, here are all the transformations of the parent function 1 over x. There's 3 different transformations to be on the lookout for. There's the a value, the h value, and the k value. Each one of these moves the graph in a certain way. Whoops, we're on the wrong page here. Let me move down a little bit. Yeah, sorry. Each one of these moves the graph in a certain way. The h value, we've already seen what the h value does in previous graphs. It's a horizontal shift. It moves it left and right. And that mainly will affect the vertical asymptote, because the vertical asymptote moves left and right with the graph. The k value we've seen before. K value always shifts the graph up and down, and that's true for this as well, and that will mainly affect the horizontal asymptote. Now, we have not really talked about what the a value does. Even though we've seen the a value in different functions, we've not really talked about what it does. But let's take a look at what it does. the A value actually causes the graph to stretch or compress vertically. So if the A value is greater than 1, it stretches the graph out vertically. If the A value is between 0 and 1, it makes the graph compress vertically. And if that A value is actually negative, it is going to reflect it across the, it's actually a vertical and horizontal reflection. It's just a reflection here. Now, if we take a look at the graph, and let's just go ahead and get Desmos out here. Now I'm going to add the transformations here, and I'm going to add sliders for all the different values. So I can change A, H, and K as I want to. So let me first take a look at the parent function. So the parent function would have A being 1, H being 0, and K being 0. Okay, no transformations whatsoever, and it looks like this. We already saw it before. Well, let me graph that so that we can compare it. So I'm just going to put that on here as this graph so that we can see how it changes. Now you'll notice if I adjust the H, it just moves the graph left and right. Okay, you can see the horizontal asymptote moving with it. Or sorry, the vertical asymptote. You can see the vertical asymptote moving along with the graph. If I move the K value, so I go down to K, you can see this moves the graph up and down. Okay, you can see the horizontal asymptote is being moved up and down according to the different K values. So when K is 1, well, now the asymptote, horizontal asymptote is at 1. Now the A value is actually what I want to talk about here. So right now A is 1, but let's move A to like 3, for instance. Well, look what happens to the graph. It's the red one. Well, none of the points, or sorry, the graph hasn't actually been shifted up or down. However, the points are different. Okay, let's compare one point in particular. So like if we look here, this point on the original graph, this was 1, 1. This point might look like it's been moved, translated up here to 1, 3. But it hasn't actually been shifted because the asymptote is in the same place. It's only been stretched up this way. So this A value is stretching this point away from the x-axis. Okay, it's pulling it vertically upwards. So this is why it's called a vertical stretch, because it's vertically pulling this point up. And it's doing it by a factor of 3. Okay, it used to be at 1, now it's at 3. So it's basically been multiplied by 3 to get up here. Now, if we change that A value to something else, like a fraction, let's make it 1/2, so 0.5, you can see the point's been stretched closer to the x-axis, okay? This point that used to be at 1, 1 is now right here at 1, 0.5. So even though the graph has not been shifted at all, the points have changed because they're being stretched, they're being compressed towards the x-axis. They're being compressed vertically downwards. So this is referred to as a vertical compression because this value is less than 1, so it's compressing it towards the x-axis. And if we make that A value negative, so let's make it -1, as you can see, the graph has been reflected. This is both a vertical and a horizontal reflection because you can either think about it being reflected over here, or you can see it reflected over here. So it's both a vertical and horizontal reflection because of the symmetry of the graph. So one of the things we're going to want to do, let me make that positive again. One of the things we're going to want to do is understand and see the transformations. So let's take a look at how we actually go about graphing by hand these graphs. So first we identify the vertical asymptote. The vertical asymptote is always equal to the h value, because the h value is the horizontal transformation, and that moves the vertical asymptote. The vertical asymptote is a vertical line, and it always has the equation x equals h. The horizontal asymptote, which is affected by the vertical shift, gets moved up or down, and it will have the equation y is equal to k. So it's always y is equal to whatever the vertical shift is. We can also graph the y-intercept and find the y-intercept by plugging 0 in for x and evaluating. We can do the same thing with the x-intercept. We can substitute 0 in for y and then evaluate. And then we can fill out our table, and basically we just plug numbers in. We plug numbers in that are to the left of the vertical asymptote and to the right of the vertical asymptote. So like a couple of values over here and a couple of values over here, so we can get an idea of where the graph is. Then we state the domain and range. So let's take a look first at the parent function. We already know what this looks like, but let's go ahead and graph it by hand. So the a value is 1, which means that there's no stretch or compression. The h value is 0, which means that there's no horizontal shift. And the k value is 0, which means that there's no vertical shift. So the vertical asymptote, x equals h, so x equals 0, and that is right here. We already saw that on Desmos. Our graph is right here. The horizontal asymptote, y equals 0. That's a horizontal line that right here, where all the y coordinates are 0. And we can basically just build our table around the vertical asymptote, which is at 0. Now, plugging in 0 doesn't actually do anything, because 1 over 0 is undefined. So we don't have a y value here, because there's no point on the graph. But we can build the table around this. So a couple of values to the left, a couple of values to the right, and we can simply plug these into the equation to evaluate. So we're doing 1 over x. So plugging in -3, 1 over -3 is just -1/3. Plugging in -2 gives us -1/2. Plugging in -1 gives us -1. Plugging in 1, 1 over 1 is 1. Plugging in 2, 1 over 2 is a half. Plugging in 3, 1 over 3 is a third. And I'm going to plot these points as best I can. So -3, -1/3 is right here. -2, -1/2 is right here. -1, -1 is right here. So we can see the graph looks something like this. And then we can go to the other side. 1, 1, 2 and 1/2, 3 and a third. So we can see the other side looks pretty much the exact same, like this. And this is our graph. Now the y-intercept, we could find the y-intercept by plugging in 0 for x. But you'll notice that when you plug in 0 for x, you get 1 over 0, which is undefined. So there is no y-intercept, and you can see that because there's an asymptote on the y-axis. So there's no y-intercept because there's an asymptote there. The x-intercept is kind of the same thing. Okay, so if you wanted to find the x-intercept, you would plug in 0 on, you would set the equation equal to 0. You'd get 0 equals 1 over x. But this does not have a solution. Okay, you multiply by x and you get 0 equals 1, which doesn't make any sense. So there also is no x-intercept, and that is specifically because that's because the asymptote is on the x-axis. So there's no x-intercept either. As far as the domain and the range, if you look at the domain, the x values, you can plug in any x value you want except for 0. You cannot plug 0 into this because that would make this undefined. The asymptote will never be in the domain, or the range. There's an asymptote in the range, there's an asymptote in the domain. So the domain is everything except for 0. So we actually split the domain into two pieces, the left piece and the right piece. So the left piece goes to negative infinity and then goes to 0. So that's the first part of the domain. And we use a u to separate the pieces. And the right piece starts at 0 and goes to infinity. This includes everything except for 0. Okay? This part includes all the negative numbers. This part includes all the positive numbers. The only thing that's not included here is 0. And we have the same thing for the range as well. The range, we split it into two pieces. So negative infinity up to 0. And then a u to separate the two pieces. And then on the other side, up here, starts at 0 and goes up to infinity. Once again, the range, everything except for the asymptote, which is 0 in this case. And that's our graph, everything we need here, and that's perfect. All right, next example, y is equal to 2 over x minus 4 plus 2. First of all, I do want to talk about the transformations. All right, the transformations that we're looking at, we actually have a shift to the right by 4. Okay, if you look at the a value is 2, the h value is 4, the k value is 2. This is a shift right by 4, up by 2. This is also going to be vertically stretched by 2, by a factor of 2. Okay, because the a value is 2, is going to stretch it out by a factor of 2. All right, so I'm going to fill all of this information out. The vertical asymptote, x equals h, so x equals 4. This is right here. Horizontal asymptote, y equals k, so y equals 2, which is right here. We'll get to the intercepts in just a second. Let's build our table around the the vertical asymptote. So I'm going to pick some points to the left of that, 3, 2, and 1. Pick some points to the right of that, 5, 6, and 7. And I'm going to plug all of these in to the equation to figure out what their outputs are. So first I'll start by plugging in 1. So I got 2 over 1 minus 4, so 2 over negative 3 plus 2. Okay, so that's like 2 1/3, or 2.3, repeating. All right, let me plug in 2. Whoops, was that negative? Oh yeah, whoops, I messed that up. Let me try that again. So plug in 1, 2 over, oh no, that might have been right. Let me double check. So negative 2/3 plus 2. 1 minus 4 is negative 3. So negative 2/3 plus 2. So that's like 1.3 repeating. Okay, that looks correct. Okay, let me plug in 2. So 2 over negative 2 plus 2. So negative 1 plus 2, that's 1. Let me plug in 3. So 2 over negative 1 plus 2, which is 0. Okay, let me move to the other side of the asymptote. So 5. So 2 over 1 plus 2. 2 plus 2, that's 4. Let me plug in 6. So 2 over 2 plus 2. So 1 plus 2, that's 3. And let me plug in 7. So 2 over 3 plus 2. So that's like 2.6 repeating. 2 and 2/3. So, okay, so let's see if this graph looks like what I expect it to. I actually expect it to be over here and over here, like the rest of them. So 1 and 1.3, which is like right here. 2 and 1, 3 and 0. Okay, so that looks correct. And then on the other side, 5 and 4, 6 and 3, and 7 and 2.6, and that also looks correct. Okay, let's take a look at our intercepts. So the x-intercept, you can find the x-intercept by plugging in 0 into the equation. So I haven't done that yet, so let me plug 0 into the equation. So plugging in 0, I get 2 over negative 4 plus 2. That's negative 1/2 plus 2. So that's like 1.5. Okay, and if we look at our graph, we can probably see that, whoops. If we look at our graph, we can probably see that, oh, whoops, that's the y-intercept. The y-intercept, you plug in 0 for x. So that's the y-intercept. Plugging in 0 for x gives us the y-intercept. So we should see a y-intercept at 0, 1.5, and we do see that right here. Plugging in 0 gives us 1.5, that's the y-intercept. Now if we want to find the x-intercept, we actually have to set the equation equal to 0. So we would have to do, let me get a blank page here, 0 equals 2 over x minus 4 plus 2. Now this is a little bit more complicated because you have to solve this for x, but it's not that bad. Subtract 2. Negative 2 equals 2 over x minus 4. Multiply by x minus 4 to get that x minus 4 out of the denominator there. So you get negative 2x plus 8 equals 2. Subtract 6. Negative 2x is equal to negative 4. Divide by negative 2. So x should be 2 when y is 0. And let's take a look if that is, or wait a minute, I think I made a mistake. I subtracted 6. I'm supposed to subtract 8. What? So minus 8 gives me 6. Negative 6. Dividing negative 6 by negative 2 gives me 3. So my intercept should be at 3, 0. My x-intercept should be at 3, 0. And we actually already knew that because we saw it in the table. 3, 0, we already had that point in the table, so we didn't actually have to do all of that work to find it. Sometimes that'll happen, and you don't actually have to do all the work to find it. The domain is everything except for the vertical asymptote, which is at 4. So that would be negative infinity to 4, and then from 4 to infinity. The range is everything except for the horizontal asymptote. So that's 2. So negative infinity to 2, and then 2 to infinity. So these two pieces, and that's our graph for number 2 here. Now most of these transformations are easy to see, right? 4, up 2, very easy to see. The only one that's not super easy to see is when it's stretched out by a factor. But these points are being pulled away from the axis. Well, in this case, it's being pulled away from the asymptote because it's been translated. All right, let's take a look at one more here. So we have our a value is actually -3, our h value is -1, and our k value is -4. Now, because the a value is negative, we actually expect this to be reflected. Okay, so the piece that's usually in this area is going to be over here, and the piece that's usually here is going to be on the other side. Okay, because the a value is negative. So there's a couple of transformations we're looking at here. We're looking at a reflection because of the negative. We're looking at a vertical stretch by a factor of We're looking at a vertical stretch by a factor of 3. We're looking at a shift down by 4. And we're looking at a shift left by 1. Okay, so there's a lot of transformations here that we have to be aware of. So the vertical asymptote will be x equals h, so x equals -1. Horizontal asymptote, y equals k, so y equals -4. So we'll go ahead and start there to try to get our graph together. So -1, vertical asymptote right here. -4, horizontal asymptote right here. We'll build the table around the vertical asymptote at -1. So to the left, -2, -3, and -4. To the right, 0, 1, and 2. And we'll plug these into the equation here to see what they evaluate to. So I'll start by plugging in -4. That's -3 over -3, right? Minus 4. So 1 minus 4 is -3. Plug in -3. That's -3 over -2 minus 4. Okay, so what's that? 1.5 minus 4. Got a calculator here. 1.5 minus 4. That's -2.5. Plug in -2. So -3 over -1 minus 4. So 3 minus 4, that's -1. Plug in 0. So -3 over 1 minus 4, that's -7. Plug in 1. -3 over 2 minus 4, so that's -1.5 minus 4, so -5.5. And then we'll plug into -3 over 3 minus 4, so -1 minus 4, which is -5. Okay, we got all the points we need. We can now put these on the graph. So let's start with the left side. -4, -3, -3, -2.5, and -2, -1. And just like we expected, it has actually been reflected. Okay, this piece used to be over here, or over here, it doesn't matter. It was in one of these two, but now it's reflected over on this side instead. The other piece should be down here as well. 0, -7, 1, -5.5, and 2, -5. And just like we expect, it's over here. Okay, because we have a reflection. So this one, we have a lot of different transformations. Let's see if we can figure out where the intercepts are here. So the x-intercept we can find by plugging in 0. Hey, we already plugged in 0. We know where the x-intercept is. Or sorry, that's the y-intercept. I usually do these the other way around. The y-intercept, we can plug in 0 for x. I keep thinking I'm doing the y-intercept, I'm not. So y-intercept is what I usually do first. And I plug in 0 for x, but if you take a look, we already did that. The y-intercept is 0, -7, and we can see that right here on the y-axis. We can see the y-intercept. However, the x-intercept is a little bit more complicated. I can't see where the x, I know it's somewhere around here, but I can't see exactly where it is. So what I have to do is set the equation equal to 0 and figure out what it is. So 0 equals -3 over x plus 1 minus 4. And I can just solve this for x to see what this is. So plus 4 equals -3 over x plus 1, multiplied by x plus 1. We got 4x plus 4 equals -3. I can solve this for x. So minus 4. 4x equals -7. Divide by 4. So x is equal to -7 over 4. So I'm not sure what, let's see what that is as a decimal. -7 over 4, that's -1.75. So the x-intercept when we is -1.75, comma 0. And that's about where this point is. Okay, we can see this point's really close to what that is. -1.75, comma 0. That's where our x-intercept is. So we can see our x and y-intercept. However, we do have to do the algebra to figure out exactly where they are. The domain is everything except for the vertical asymptote. So from -infinity to -1. And then the other side of the vertical asymptote from -1 to infinity. The range is everything except for the horizontal asymptote. So from -infinity up to the asymptote at -4, and then from -4 to infinity, from the asymptote up to infinity. All right, so this is how we graph rational functions here.